Okay, good afternoon, everyone, and welcome to our webinar on multiphysics modeling of Joule, induction, and RF heating. My name is Mike Huron. I'll be the presenter today. Why don't we go ahead and get started? So first up, if we have any questions during the webinar, please use the chat feature and send along your question. I'll do my best to recognize and answer those as we're going. And please note that the webinar will be recorded for today. So plan for our next hour or so is to do a brief introduction to Verist Engineering. We'll cover a review of electromagnetic heating principles, and then we'll use two case studies to illustrate how we model these types of systems in COMSOL multiphysics. So we'll first talk about a catalytic reactor and how we can model Joule, induction, and hysteresis heating in a system that has chemically reacting flows. And then we'll talk a little bit about the RF heating of a process fluid in a microwave cavity. And finally, we'll wrap up with some Q&A as needed. Okay, so a little bit about Verist Engineering to get started. So we are located outside of Boston in Massachusetts. We were founded in 2006. We are a technical consulting firm with expertise in engineering, mechanics, and material science. So we have 12 folks currently on our technical staff, with greater than 80% of us having PhDs. We have a 3,000 square foot mechanical test lab where we have specialized expertise that we've developed for the testing and modeling of polymers, adhesives, and other strain, rate, and temperature and environment dependent materials. As a consulting company, we engage with a number of clients in industry, in academia, and in the government. And as a part of that, we transfer all methods, models, and data, including any IP generated as a part of our engagements, to our clients. And one thing that we like to describe ourselves is that we offer academic level expertise at an industrial time frame. And so we work on a lot of really tricky, rigorous problems, but we do that with an eye towards industrial and commercial timescales. Broadly speaking, our practice areas, what we call our practice areas, are what we show here. So materials engineering, we have expertise specifically in the areas of polymer mechanics. And we have in-house analytical tools where we help advise our clients on material selection, material suitability, and material quality control for their product development purposes. We have a mechanical test and material modeling practice. We've developed some specialized expertise, as I mentioned, in the testing of nonlinear materials. We've developed our own in-house test capabilities, including drop towers and high-rate test systems to capture complex nonlinear constitutive behavior of those materials. Almost always an outcome of our work in the lab is a constitutive model for a finite element analysis model. So we work with a lot of clients to develop constitutive models that then either they or we will use for modeling the system or component behavior in a complex manner. And that leads us kind of into our multiphysics simulation practice, of which I help to lead. Our multiphysics simulation practice is a collection of experts in heat transfer, fluid mechanics, solid mechanics, and electromagnetics. And we work together to solve complicated nonlinear multiphysics problems for our clients that involve one or more of those individual physics. And so some examples of that include chemical reactions and turbulent flow in vortex mixers, or combustion and heat transfer near combustor liners in that top figure there. Finally, our failure analysis practice, which draws on all our other three practice area capabilities, is something that we do at the behest of both industrial and legal clients to help understand product failures, identify root causes, and make recommendations for product improvements. Here, we articulate our specific areas of subject matter expertise, and what these really represent are individuals within our firm who have a deep training and fundamental understanding of the physics and engineering science and material science behind these areas, from solid mechanics to fluid flow and reactions to electromagnetics and heat transfer through materials and material testing. And so as a firm, we offer a kind of a complementary skill set and team to aid in our clients' product development activities. Okay, so that's a little bit about Verist engineering. Next, we'll dig into the principles of electromagnetic heating, just to kind of set a baseline of what exactly we mean when we talk about electromagnetic heating and the different physical mechanisms that present themselves in electromagnetic heating systems. So the first thing to cover is the electromagnetic spectrum. And so what we refer to here is the frequency at which electrical or magnetic fields operate. And so on the left-hand side, we have our direct current part of the spectrum. And so steady state direct electric potential type of fields. And an example of that would be a resistive heater, such as a Cal rod, which may be used in an oven or some other heat processing system that you may commonly encounter. As we move from the left hand side of direct current into alternating current, we move into the low frequency, what we call low frequency portion of the spectrum. And I'll caution that there's kind of no hard and fast rules to kind of where one part of the spectrum begins and another ends, with the exception of direct current, of course. There is often overlap between, for instance, RF and microwave portions of the spectrum. And so in the low frequency portion, which is typically 30 kilohertz, maybe a little bit higher than that and down, we have typical devices such as induction heating, where in the example that we're showing here, we have a coil wrapped around a metal workpiece. And by applying an alternating current, we can induce a current on our workpiece through that time-varying field. Moving to the right, we move into the radio frequency domain, which is above the low frequency domain, but below the kind of a few gigahertz type spectrum frequencies. And a common application here is that of RF tissue ablation. And so that's the example, if I show this animation again, of applying an electrode to tissue in the body and applying a RF electromagnetic field to provide localized heating to eliminate or abrade tissue, either in cancerous regions or in blockages in arteries and veins, for instance. Moving to the right, we get into the microwave regime, which is kind of upwards and above of the RF regime, and is typical of, for instance, the microwave you may have in your kitchen. or other industrial processing systems that rely on microwave heating for raising the temperature of dielectric materials. And finally, all the way to the right is the infrared um, spectrum, where we consider things like thermal radiation, which we can see in the finned heater on the bottom right, where thermal energy is transferred by infrared waves, and is very commonly encountered in many different types of heat transfer problems. For the purpose of today's um, for the purpose of today's discussion, we will be focusing on the kind of everything that is below the infrared regime, so the microwave, RF, and low frequency portions of the electromagnetic spectrum. So let's talk about how these electromagnetic waves actually generate heat. And there's primarily three mechanisms. So one is electric current passing through a conductor by an applied electric field, or that is induced by a time-varying magnetic field. And so this you can kind of think of as the resistive heating that occurs due to the resistance of electron flow in a conductor, or a non-ideal conductor, I should say. The second mode is hysteresis losses in magnetic materials. And so how does the material respond to a time-varying magnetic wave? And finally, the excitation of polar molecules. And we'll talk a little bit more about each of these in detail in the following slides. But at the fundamental level, the manner in which these work is that kinetic energy is transferred from the electromagnetic signal to the molecules of the heated material. And that can be done by collision or by oscillation from a magnetic wave. Kind of thinking this through a little further, the temperature of any bulk material is essentially proportional to the mean kinetic energy of its particles. And so as we're transferring energy from time-varying electromagnetic waves, for instance, into a conductor, that is essentially what we're doing, is we're making the molecules oscillate or move or collide with one another, and thereby increasing the temperature. So let's look at just a pictorial of how these mechanisms work. So the first mechanism that we mentioned is the Joule or resistive heating. In this case, charged particles, which we indicate in blue in the animation here, travel through a conductor that has a finite resistivity or finite conductivity, and they collide with the current carrying material. And so that's the dots in red. And so that collision is the transfer of kinetic energy from the charged particle to the conductor at the microscale, which is, the way that we observe that is essentially an increase in temperature at the macro scale. And so this is a pretty straightforward mechanism whereby this collisional activity leads to an increase in temperature. The second mode is what we call induction heating, and this is really a special case of resistive heating. And the reason we say that is essentially we are still generating heat in much the same way, in that we're inducing a current in the workpiece, which we show in gray on the right. But the way that we do that is a little bit different than in the previous example. So in the previous example, we applied an electric potential across two ends of a conductor. In this example, we use a non-contact method whereby we pass current through a coil that surrounds our workpiece. That time-varying magnetic field induces an electric field in the workpiece, and the current will follow basically that induced field. And so same principle in terms of how the electricity is, the electromagnetic heat is generated, but the manner in which the field is generated in the workpiece is done in a slightly different way. Now, of course, if the workpiece is ferromagnetic, we may also experience hysteresis losses, which we'll discuss in a few slides here. Next, we talk about dielectric heating. So dielectric heating is occurs when high frequency AC electric fields induce molecular rotation or excitation in polar molecules. And so you can think of this as applying most typically to water molecules in your microwave. What happens with a water molecule when an AC electric field passes by is that it rotates in response to the polarization of the molecules and with respect to the electric field. And so that's what we've tried to draw in our little cartoon representation here is the vibration or rotation of the molecules in response to the electric field. And that rotation or excitation of the polar molecules raises the thermodynamic temperature of the excited material. Now, RF and microwave heating share essentially the same physical mechanism, with RF having a longer wavelength and therefore the ability to penetrate deeper into material than microwave typically has. Finally, we talk about hysteresis losses. Now, hysteresis losses are a characteristic of ferromagnetic materials that follow a different magnetization curve in the presence of alternating fields as the field changes direction. So this is fundamentally a property of the material. And magnetic fields, what happens in this scenario, helps to align dipolar molecules, magnetizing the material. And then when the field is reversed, so too are the dipolar molecules, and heat is then dissipated. Hysteresis loss, therefore, is a function of the material and specifically the BH curve. And now there's a number of ways that we can implement this into a model, but fundamentally what we're interested in is the area under the curve within the BH curve that represents the heat dissipated per cycle. Okay, so that's a little bit about the fundamentals of electromagnetic heating. Now let's look at a few examples of modeling electromagnetic heating in console multiphysics using two toy test models as a means of describing how we model this type of phenomena. So the first example that we'll talk about is steam methane reforming. So steam methane reforming is a common manner in which hydrogen is generated from natural gas and oil. So today, 80% of hydrogen is generated in this manner. And typically, these processes are driven by burning natural gas. So steam methane reforming is an endothermic process, meaning that it requires heat input to drive the chemical reactions forward and produce hydrogen from natural gas. And a conventional reformer is shown over to the right. So we have a methane that flows through long vertical tubes that are packed with a catalyst. Within that catalyst, the methane flows and is heated from the outside, which is provided by firing natural gas in a very large burner or boiler configuration, whereby the tubes are heated primarily by radiation. So this is a well-developed method. It's been used for many years and is quite mature, but suffers from a technology perspective from significant drawbacks. So one is that this is generally thermally inefficient. So the temperature at which you need to reach to reform methane is around 800 to 900 degrees Celsius. The temperature of burning natural gas is going to be much, much higher than that, maybe 2000 degrees Celsius. Additionally, we're heating from the outside, and so that heat has to propagate into the reformer tubes, which is balanced by heat that's lost to the environment. And finally, by burning natural gas, we're generating emissions that are undesirable from an overall performance perspective, and are something that there stands to reason could be improved by electrifying such a process. So some work has been done in this field, and we'll explore a little bit about what that looks like and how we do that in COMSOL. So electric heating is is a way that we could potentially increase efficiency of these types of systems by providing more targeted heating, reducing emissions, and importantly, improving thermal uniformity in the reforming tubes. So a few ways that in the literature that we see people exploring the electrification of SMR include resistive heating of the reformer tube. And so that's what we show on the right, basically connecting the reformer tube into a direct current circuit, applying a current across that circuit and generating heat. Similarly, induction heating of a susceptor that is internal to the reformer tube. And finally, hysteresis heating of ferromagnetic catalyst particles, which provides for a more distributed heating mechanism. So we adapt a reactor described in the reference shown below and explore how each of these three heating mechanisms work and what are the equations that we're solving in COMSOL to understand the reactor performance. So first, let's talk about the resistive heater. So as I mentioned a moment ago, the heater is shown on the left here, where we have copper leads that connect into the reformer tube, which we've scaled down by a factor of 10x for this image. We apply an input current to the electrical circuit and model the gas flow through the center of the tube, which interacts with a catalytic washcoat or porous media along the walls of the reformer. So what we're solving in terms of our COMSOL model here is the electric potential equation. So that's the first equation shown on top, where the conductivity of the material, both the copper leads and the ink alloy tube, is a function of temperature. And then in the solid domains themselves, we're solving for the thermal conduction equation. And so where we get coupling between the electric circuit and the heat transfer equations are through the temperature dependence of the electrical conductivity of the material. Now, in the gas, we're solving for the Navier-Stokes equation, so the conservation of mass and momentum, along with the conservation of energy and the conservation of species. So at the inlet of the reformer, we have by volume fraction 30% methane, 10% hydrogen, and 60% steam. And these couple together through the energy equation and the reaction terms. So we list here the SMR kind of global reaction equations. And as you can see, those are strongly endothermic, meaning that all the energy we're generating through the resistive heating of the ink alloy tube is used to power or basically provide energy to the endothermic SMR reactions. And so we solve this fully coupled set of equations, the electromagnetics, the flow, the heat transfer, and the species in COMSOL in a fully coupled manner to predict what does the temperature rise and the methane consumption profiles look like in a reactor that's constructed in this manner. And so what we plot in our contour plot here is on the top, we plot the temperature distribution. So you can see flow coming in from the left and exiting at the right-hand side of the reformer. And all of the heat is supplied through the outer wall of the reforming tube, because that's where we are applying the current, and therefore that is where heat is being generated. So we have strong radial and axial temperature variation in this system. And we can see that the methane mass fraction follows a very similar profile in terms of its consumption. And so we get, for this specific scenario, rather weak consumption and strong temperature gradients in the reactor that are otherwise quite hard to control. Now, on the right-hand side, what we're showing is basically where does the heat come from and where is it consumed. And so all of the Joule heating occurs in the wall of the reactor. That's this red region of our chart here. And all of the heat is consumed in the porous washcoat, more or less, where where the reaction is occurring. And so one of the downsides of this type of electromagnetic heating, similar to the gas-fired heating with a conventional system, is that all of the heat is applied from the outside in, and we develop strong temperature gradients and have to therefore create temperatures much hotter than we otherwise need to generate or to drive the steam methane reforming reactions. So let's look at how we could change this type of system to be a little more efficient by leveraging induction heating. And so here in this example, we adapt our previous reactor to leverage the induction heating of a solid susceptor. So we modify our system by placing a soft iron susceptor in the center of our reforming tube surrounded by our catalyst. We surround the tube with a coil that's excited at 70 kilohertz, and we use that coil to induce eddy currents on the susceptor and drive the heat generation rate such that heat is being generated at the center of the reactor, which then has to propagate outwards. So we update our model, and we move from modeling the steady state electric potential equations in the Joule heating example to modeling the time harmonic Maxwell's equations for this low frequency induction heating example. And so what we've listed in our equations here are the Maxwell's equations that we solve to describe the electromagnetic system, and their coupling to the steady state thermal conduction in the solid domains. Everything about the reactions and the fluid flow remains the same. The primary change here is that we have two terms in our thermal conduction equation. So the first is our resistive heating, or our Joule heating term. That's what we show in bold here. And so that's going to be dominating in this scenario at low frequency and in a susceptor that is long enough for or big enough for currents to be induced. And the second term is our hysteresis loss, and which for this specific scenario we ignore, but we'll revisit in our next example. So let's look at how this system works. Again, we solve this in a fully coupled fashion in COMSOL Multiphysics. We apply an AC current excitation through the coils. And that applied current induces a current in the susceptor. And what we'll notice on the left-hand side here is that the heat generation rate, which is, again, proportional to where the current is being induced, occurs in a very thin region near the surface of the susceptor. And so you can see we're plotting on log scale the heat generation rate on the susceptor due to the induction heating. And so what's important to recognize about this type of simulation from a practical perspective is that our mesh needs to be able to refine or capture what we call the skin effect region. And we can calculate or get a rough estimate of the skin depth based on the excitation frequency and the material properties of the susceptor, which tells us that in this particular scenario, the skin depth is about 25 microns. So we get this current that's induced on the surface of the susceptor. Here we see the direction of the current that is generated, which is circumferential. And that strong heat generation rate, that strong current that's induced generates heat, which then has to propagate out of the system or heat the system from the center outward. So if we again look at what how the reactor performs in this scenario, and we think back to what our temperature field and methane conversion fields look like from our previous example, what we notice right off the bat is that the temperature field is much more uniform. We still, of course, have the axial gradient as we're are heating just in a portion of the system. But our radial gradients have been reduced quite dramatically. So we have a much more consistent or uniform temperature field in the bulk of the catalyst region. And the methane consumption is more efficient because of that. What we plot on the right is basically how the heat of reaction balances the heat induced in the susceptor. And so you have, again, in log scale, a very sharp concentration of the heat generation rate near the surface. This vertical coordinate is the normalized radius. So you have a sharp collection of the heat generation rate near the surface of the susceptor, and that balances heat reaction, which occurs distributed through the catalyst, the porous catalyst bed. So this certainly improves from a system performance, the uniformity of the temperature field and the overall conversion rate of methane because the temperature is much more uniform. Okay, next we'll talk about how we can further improve this type of system. The susceptor kind of moves us in the right direction in that it helps to promote temperature uniformity. However, the solid susceptor is prone to fouling, and the coupling efficiency, or the efficiency or the amount of energy that gets transferred from the coils to the susceptor, is proportional to the radial distance between the susceptor and the coil. And so what that means as a consequence is that scale up becomes challenging for this type of system. So here, what we evaluate is a scenario where we leverage magnetic hysteresis heating of ferromagnetic catalyst particles. And so there's been a lot of research done on catalyst properties and particles that can act both as a catalyst for specific reactions, as well as an electromagnetic susceptor to generate heat to power those reactions. And so cobalt nickel particles are one good example of a reasonably well developed, from a technical perspective, catalytic particle that can also be heated. So here again, we model very much this similar physics, but we note that for particles that are small in size, where current cannot really be collect and generate due to the small surface area of the particulate, what dominates the heat generation rate in this scenario is the hysteresis term. And so that's these magnetic losses that are shown in bold here, which we can model in a number of ways. In this specific example, we model using data from the literature that provides a complex permeability, electric permeability of the particulate matter. So again, modeling the same general system in terms of the kind of flow rates and composition of the inlet. Here we excite the coils at a higher frequency, which we find to be more effective. And again, plot the distribution of both the electromagnetic heat as well as the heat of reaction. So on the top-hand side, we can see that the thermal gradients have further improved. The temperature is almost uniform, both axially and radially within the catalyst region. And the reason is we're generating heat in a distributed manner. So the heat, the susceptors are distributed, and anywhere that there's a susceptor, we're generating heat in response to that magnetic hysteresis loss. And we see a much more efficient and uniform consumption of methane as a result of that. And so this is largely improved kind of the overall performance of this type of system by leveraging hysteresis heating. And again, solving all of this kind of in a fully coupled manner within COMSOL multiphysics. Okay, so that is a little bit of exploring how heating works for kind of the fundamentals of heating for both Joule, inductive, and magnetic hysteresis heating. Now let's switch gears a little bit and talk about RF heating of a process fluid. So this example is a different test case and takes after something that some work that we've done here at Verist and with one of our partners in heating process fluids. And so, as an example of this, the chemicals industry uses, approximately 2,000 tera-BTU per year, heating fluids to low temperatures, so less than 150 degrees C. And microwaves can be quite efficient at doing this. And so the example that we're going to talk about here is using a microwave cavity and a tuning which is comprised of a waveguide, a tuning rod, and a resonator cavity, and flowing water through that microwave cavity to collect heat and exit at an elevated temperature. Now, the physics that we're modeling here are at higher frequency. So here we're at almost a gigahertz, or a standard microwave frequency of 975 megahertz. And so for this type of analysis, we model the time harmonic Maxwell's wave equation in the frequency domain. We couple that to the steady-state thermal energy equation, whereby the source of heating is proportional to the complex permittivity, or the loss tangent, of the material. Now, in general, the loss tangent can be quite sensitive to the temperature itself, so these are often temperature dependent. If you ever tried to microwave water, it's a very good receptor of RF energy or microwave energy up until the point where it boils, after which it is a very poor receptor of microwave energy. The first step we take in modeling this type of system is to optimize the cavity itself. So the performance of this system is very much sensitive to the dimensions of the cavity. And so what we do is we parameterize the cavity shape and predict the loss coefficient, or the S11 parameter, to understand its response with respect to the cavity dimensions. And so this is purely from an electric field perspective. And what we find is that the loss coefficient, or the S11 parameter, changes sharply with the cavity dimensions, and we have very localized minima. So you can see there's a very specific location within this field of possible parameters whereby the cavity is efficient. But once we reach that, the loss is vanishingly small for an isothermal system. So we identify what the optimal cavity shape should look like. And from there, we couple the electromagnetic flow and heat transfer equations, solve them in a fully coupled fashion in COMSOL multiphysics, and predict our loss density, electric field strength, and ultimately water temperature rise. And so what we find in this scenario, and which is quite interesting, is that the temperature reaches nearly 100 degrees C by time we reach the outlet of just this one sector of the cavity, and that approximately 92% of the input energy is absorbed by the water. And so what's interesting about that is that we tuned this cavity for basically room temperature conditions. And so the change in the loss tangent as a function of temperature can have a very big role in reducing the efficiency of the system just by going from room temperature to close to 100 degrees C. That would change the kind of desired shape of the cavity. So if we were to do this in a more detailed fashion, we would run the cavity optimization in a fully coupled manner as well, rather than optimizing around room temperature, for instance. Okay, so just to wrap up and leave a little bit of time for questions, we talked today about kind of the fundamentals or the basic principles of electromagnetic heating, and the primary mechanisms by which heat is generated, which include electric current passing through a non-ideal conductor, hysteresis losses in magnetic materials, excitation of polar molecules through RF or microwaves. And then we studied a few case studies that leverage the above forms of electromagnetic heating coupled to other nonlinear physics to demonstrate how multiphysics simulation can help guide design and development of these type of heating technologies, and how COMSOL multiphysics in particular enables a fully coupled modeling and simulation of these complex and nonlinear heating technologies. So with that, I thank you for listening in today. And if you have any questions, I would be happy to take them now, or feel free, please, to follow up with me offline, and I can address them there as well. Okay, well, if we have no questions for today, thank you everyone again for your time. And again, please feel free to reach out offline. Be happy to chat.